delighted to introduce Professor Eduardo Martin-Martinez. He will tell us about relativistic measurement approach. Eduardo is from Waterloo, from the IQC, also, as you can see, affiliated with the perimeter, originally from Spain. And if you look at his contributions, yeah, very rich and interesting and broad in the foundational and then also more applied questions in quantum information science. This is really just I learned a piece of his research, also work on quantum thermodynamics and what else did you mention? Quantum communication. Oh, okay, the next slide, you learn about the different areas. So thank you so much for taking the trip here and hope to learn about the work.
All right, thank you so much for the invitation and the nice introduction. Thank you both of you for having me here. And it's my pleasure to give you a little talk about, I had to pick a topic, so I went for a more foundational one, but I'd be happy to chat with anybody about any of the other things if you're interested. Let me tell you one thing, format of the talk, I am extremely happy to be interrupted and discussion. And if I don't finish, I don't finish and I don't mind. The talk will start hopefully like not too difficult to follow. It become more technical and specialized as we go. So if I don't finish, I don't care. Make sure that you don't get lost and you ask. I'm happy with the discussion. I think that's the best and most fun part of the talks for the most part. All right. So let me show you a little bit. This is the people that has been involved. All were my students except for Luis. He was actually my professor when I was an undergrad student. Everybody else were students of mine. Actually, all of them graduated. Some of them to different levels of how recent, very recent, relatively recent, between both. So anyway, so yeah, I like to say that my work is in the field of relativistic quantum information, which is something that is a very diverse field. So if you ask me what is relativistic quantum information, I could tell you, well, that's a tough question because there are many people, many diverse people doing many different things working in relativistic quantum information. So we don't all work on the same things, which makes it very fun when we get together, I think. But the idea is that it lives in the overlap between quantum information theory, general relativity, and quantum field theory. It's got relationship with the theory of the light-matter interaction. It's got relationships with quantum gravity. It's got relationship with algebra, with the foundations of quantum theory. Of course, overlaps with the quantum information theory and quantum technologies. So anyway, it's a very diverse field. And I also mentioned here quantum thermodynamics, which I also work in topics related to quantum thermodynamics, some of them overlapping with relativistic quantum information, some of them not. And then also I always include here the relativistic quantum optics part, which is, I like to say, in fact, it was actually, it was John's first work that inspired me to call it that a little bit, which is the idea. It's kind of funny when you talk about it and people tell you, what do you mean? But listen, there's two typical answers that you get when you, two typical reactions when you talk about relativistic quantum optics. One of them is that, what do you mean? What do I need to care about relativistic stuff if I'm doing stuff in my lab? And then you say, well, I mean, and then the other one is, well, why? Of course, quantum optics is already relativistic. It's light, which is obviously relativistic. So it's interesting, right? Because you get the two extremes of the answers. But the idea is that in the models that we use nowadays in quantum optics, in the light-matter interaction, there are many assumptions that lead to the models that we use. Some of them are incompatible with the relativistic nature of the theory that fundamentally comes from. And that means that there are some regimes where we do interesting experiments, or we could do interesting experiments related to foundations, quantum information, and quantum optics, where the approximations or the assumptions made break the theory in ways that is not okay. Yes, it's a quick summary of what that is. And I'm going to talk in this talk in particular about the measurement problem, and not just the measurement problem as the usual one. So I'm going to summarize a bit of the measurement problem, the usual measurement problem, but this is a different thing. It's a relativistic. When you add relativity to quantum mechanics, and the measurement problem becomes much more difficult. So let me just preface it by saying that it's not that the measurement problem in regular quantum theory is an uncontroversial solved matter. It's not. It's still an open problem in many ways. So I can make a proposal, right? And then you tell me, if you disagree with something I say, please tell me and we discuss it. I think the proposal is reasonable, but that's me. At least some measurements can give values. So if you're in a lab, sometimes you write down a value when you measure something. And in quantum mechanics, when we do something like that, think of a Stenger-Lach experiment as a classic experiment that does that. in which you have two possible outcomes for the direction of deflection of a beam of electrons, right? So we model that, the action of having measured that. If the measure doesn't destroy the system still exists and it's a quantum system. We model that with ideal measurements, which is, well, in a very simplified case, it's just apply a rank 1 projector over the spectrum of the observable that you're measuring. So project, no? What they teach you in the first quantum mechanics course is project, collapse, whatever you want to call it. Now, of course, there are problems that I'm not going to talk much about. So what I call quantum to classical transition is, again, a very loaded term. It could mean different things. It could be how quantum systems lose their quantum behavior when they become macroscopic. The one I'm referring to here is how do they're not unrelated, the two ones that I'm talking about. The one that I'm going to talk about is, well, how do I go from a superposition in the sense that that the outcome of my experiment is not determined. The outcome is given as a probability distribution over possible outcomes, but in the end, I observed one of them and I wrote down a number. So how did that happen? How do you go from something that is intrinsically probabilistic to actually a concrete outcome, right? This is something that in classical mechanics is solved very easily, right? If you have a statistical mechanical theory, you say, well, sure, if I do a single measurement, I can observe a value. And that is because, of course, whatever microscopic systems I have, they have a determined value to begin with. And that's when I'm catching in that particular instance. But in quantum mechanics, you can't really say that and be happy. There's some people that try and do it very elegantly, like Valentine, that would tell you, well, maybe single shot measurements don't exist, are not physical, and it's really ensembles, all that exists. But again, it's an open problem. And then at some point, right, you have to say that at some point in your chain of measurement, right, because you can say, I measure a system by coupling another quantum system to it, a detector, and then something couples to the detector and measures the detector, and so on and so forth. But in the end, you get a number, the computer gives you a number. At what level does that happen? That's what we call the Heisenberg. At what level do we treat measurement apparatuses as objects that are outside of the world, of the realm of quantum mechanics, and just give you a classical value out of a quantum state? No? But then again, those are the problems that I'm not going to talk about, because in fact, you can just, if you are not into foundations, people in foundations make a big deal about these things. I mean, you can, if you search for collapse models, you find all sort of crazy theories. And not so, I shouldn't say that, it's being recorded, and not so crazy ones too. And but still, you can just be an operationalist, right? And say, well, I'll just apply my projective measurements when I need to, and it works, and I can devise protocols, and I can have a quantum computer, no problem. Okay. But how about if we go relativistic, and in particular in QFT, in quantum field theory? Well, maybe you want to do a measurement, right, that is very similar to what I said before. Say that I want to measure a localized observable of the field. So I have a quantum field, say the electromagnetic field, and I want to measure the field amplitude, the electric field amplitude, to make it even easier, in this room during the duration of my talk. This is a region of space-time. And then it's not unthinkable that if I have a little machine that measures that, it gives me a number, maybe like 42 volts per meter, which is the right order of magnitude. Now, the question is whether we can get away with that operationally and be happy within the framework of quantum field theory. Now, to illustrate what there are issues before getting into a bit more technical stuff related to QFT, let's go back to a very basic relativistic principle, which is the relativity of simultaneity, right? So depending on, so we have here the perspective of 3 observers. All of them are at point B. The difference between them is that they have relative motion with respect to each other. There's one that is co-moving with the axes that are not like that. One that is co-moving with, let's say, this axis, one that is moving to the right at 1/3 the speed of light, one that's moving to the left with 1/3 the speed of light. And I'm here using the planes of simultaneity for the 3 observers, place of constant time for the 3 observers. Well, as you can tell, you have 3 events, A, B, C, happening in well, A and C in particular. B, let's say, is the perspective of our observers. Whether one happens before the other, if they're space-like separated, whether one happens before the other depends on the observer. So in particular, right, if you had imagine that you have something like an entangled state like that, and one part of the system, one subsystem is owned by A, another one is by C. The usual, let's say, popular science answer of, well, whoever measures first collapses the state for the other person makes absolutely no sense in this setup, because who's collapsing what? Nobody measures first here. There's no notion of who measures first for events that are space-like separated. So if you want to, so the first question that you asked, this is even not doing QFT. Imagine that I want to do just regular quantum mechanics and describe a state update for events that are space-like separated or put in space-time. How do I do the state update? Well, that's a question. It's more important in QFT, but that's a question I'm not going to really talk much about. Once again, I'm going to talk about something more basic. But if you want, you can see this. This is our attempt to. This is an old problem. People have this problem. People like Helwig, Haronoff. Anyway, we have none of them satisfactory. We had our attempt here, so if you want to check it, yeah.
So, okay, what if I'm like a really hardcore operationalist and I say that the quantum state doesn't really matter? The only thing that matters are the measurement outcomes and the correlations. And then it's completely irrelevant which measurement happened first.
Yeah, but then again, you have to give me rules for updates, of your correlation function.
You can do it in any reference frame and give the same result in terms of correlation.
So that requires, so yes, I agree with you. So if you have what is done here is, let's assume that what you say is the right way to do it. And I want to build something that represents a state, meaning like it's not the quantum state. I can upgrade the state to actually be an object that works well under this and reflects the correlations that way. You're right. That's the right way to do it. I would say it in quantum mechanics. What you'd be missing though is what is the, so you see, you should not be able, here you need to assume something else, meaning that I have a notion of relativistic causality or event locality, if you want, meaning that there's some theory up there that is not part of my quantum mechanical theory that tells me that there's causal structure. And there's only some events I can signal to, which in quantum mechanics you have to do, because quantum mechanics doesn't have a notion of, it's an interesting thing. Quantum non-relativistic, yeah. Non-relativistic quantum mechanics has a notion of system locality, but doesn't have a notion of event locality. And in fact, conflating the two is problematic. If I were talking about experiments, gravity-induced entanglement experiments, that matters a lot, the distinction between event locality and system locality. So for the formulation to work without problems, you would say, but relativity is imposed by God on my correlations. It's not coming out of a fundamental theory from axioms. In QFT, it comes from axioms. So in QFT is the only theory, well, not the only, but the only theory that we use, where you link the system locality of quantum mechanics with the event locality of relativity by a microcausality condition. So short answer, you are completely right. In this paper, what we do is precisely, can we upgrade the state, the usual density matrix, to take into account, to construct a bookkeeping method to actually have something that I say, I call that the state. If I want to call it a state, I call that the state, and this is the update rule. But anyway, yeah, that's very nice. This is not what I'm going to talk about either, but I'm glad that people are interested. Yeah. Okay, I go back to the past, to the 90s, and this is to motivate. I should go even more, but I don't have it here. So the whole, let me tell you before telling you this, don't bother too much. We'll read it together. Back in the day, when people let me go back to the times of Whiteman, early 20th century, and people are trying to learn, like the 50s and 60s, I mean, we're trying to understand QFT. You see, QFT is pretty new-ish, and QFT was made by physicists, and that was a bit of a problem, because the same happened with quantum mechanics. Quantum mechanics was made by Planck and many others after, right? But it was very physical. And then von Neumann has to arrive and say, okay, hold on. Let's try to organize this and let's make sure that we know the objects that we're working with formally. Neumann would be to QFT what von Neumann was to quantum mechanics, and starts a discipline that was called originally axiomatic QFT, and now we call more like algebraic QFT, which is the idea of, can we formulate the same way we have the postulates of quantum mechanics? Can we have a postulate for QFT? What are those? What are the minimum set of assumptions that we need to make, and where they come from? And what do they mean? At what level of math, if we want to represent them, do we need to impose those, right? And then we go to the theory of C-star algebras, and then von Neumann algebras, and the classification of von Neumann algebras, which is It's an interesting thing that you have to, I don't know if you've heard about that, but you have a von Neumann algebra. Think of the observables, it's a bit more, but think of the observables in quantum mechanics, your algebras of observables. Well, there are different kinds of them, and some of them are trace class operators, and they have a spectral decomposition, a spectral theorem, you know, as a sum, or if you want an integral of projectors, and you can talk about measurements very nicely because one eigenvalue per projector, and that's very nice. If there's not degeneracy, there is degeneracy with several projectors, but still a projector over a larger space. Well, you can have type 3 algebras. Type 2 is a bit worse in the sense that you may not have bounded operators anymore, but you may have still projectors like the spectral theorem you can generalize. Type 3, you don't have either. Those are tough algebras. Turns out that in QFT, the local observables, meaning that the electric field in this room during the duration of my talk, if you localize an observable in space and time, those things are type 3 algebras. The algebras of local observables are the not great, so the most difficult kind in the von Neumann classification of local algebras for a QFT in general. I mean, there are restrictions of QFT that you can have. For example, you can put it in a cavity and things like that. But in free space, and this is the a nice theorem by Redhead that actually shows it very nicely using the axioms. Maybe I'm not gonna get into that for time reasons. But the idea is that it is tough in QFT to have algebras of which you can actually write an observable if you want as a spectral decomposition, as a sum of eigenvalues and projectors. Now, I don't have the paper here, sadly, but oops, sorry. There's a nice paper that I showed last time I came, which is I saw the headline, which is in defense of dogma. People try to solve these problems, saying like those are mathematicians trying to do formalizing the theory. But you know, people have been doing relativistic quantum mechanics for a while, and it kind of works. And among the people working in axiomatic QFT, there was a saying, right? If you want that, no, you cannot do relativistic quantum mechanics. The notion of relativistic quantum mechanics assumes that you have something localized, something like a particle, like electrons, relativistic electrons, or photons, if you want. And those things cannot exist. And for a while, that was called a dogma, because basically everybody said, well, talk to Weinmann. Weinmann will convince you. And Weinmann would convince you if you talk to him. But there was no proof that the relativistic quantum mechanics doesn't work, that you really need something like QFT, not enough with relativistic quantum mechanics. And there was a paper by Malament that I don't have here, that the title is In Defense of Dogma. I totally recommend if you're into that. It's called In Defense of Dogma, why can't there be a theory of localized relativistic particles? And it's called In Defense of Dogma because everybody called it the dogma, because nobody proved it before and everybody believed it in the community. So anyway, relativistic quantum mechanics is not enough. Going below type 3 is foundationally tough in relativistic quantum mechanics. You need to go to QFT, and that has consequences. There's this paper by Raphael Sorkin. We're gonna partially read the abstract. It's called Impossible Measurements. That gives the name to the problem, by the way. If you ask in RQI or in QFT what problem I'm talking about, people will say, oh, the impossible measurements problem. It's because of this paper. Here said, when it's shown that the attempt to extend the notion of ideal measurement to quantum field theory leads to a conflict with locality. Super loaded word. Locality meant here as event locality, relativistic locality in particular. Okay, the fact that there's a semi-order, partially ordered set of events, right? That some of them are causes of others, can be causes, but other ones don't. Basically, there's a causal structure. Okay. Because for most observables, the state vector reduction associated with ideal measurements, like the usual apply a projector, acts to transmit information faster than light. Two examples of such information transfer are given, first in the quantum mechanics of a pair of coupled subsystems, and then for the free scalar field in flat spacetime. That's the one that matters. It is argued that this problem leaves the Hilbert space formulation of quantum field theory with no definite measurement theory, removing whatever advantages it may have seemed to possess. Well, that's the advertisement. Let's the problem stated, the proposed solution, let's not read it for now. Bit biased, but it's there for you if you want to read it. Now, quick summary of the paper. It's a very simple paper in terms of understanding what it's doing, right? It gives two examples. One of them should not be surprising, and the other one may be a bit more surprising. Number one is, well, it says, consider a 2-qubit system, say, start in a state like that, perform a local unitary only on A, make an ideal Bell measurements, right, that say that the result of that is the states, right, that they're associated with that state. Then the expectation of observable B of an observable on B gains information from the unitary on A. So the expectation value of observables of the qubit B would know about the unitary on A. Surprising? Not really. The reason is that you did something non-local here, right? In quantum mechanics, nothing forbids you. In non-relativistic quantum mechanics, nothing forbids you from doing this operation. There's nothing bad. This projection is non-local. So this projection is transmitting information. Agreed? Yep.
But it's a non-local project, so like you do the measurement on the side of B and A, and so to get the information of the measurement, you need to get the results of measurement on two sides.
This is how you fix it in non-relativistic quantum mechanics. You say, well, you need to actually send the information from one side to another. It's not possible to do it before. But that is, once again, an external thing. Meaning nothing in quantum mechanics tells you that there's a limit in the speed of information. I mean, some things do, but the connection between that and the fundamental limitation of relativity is the one thing that's missing from quantum theory. I agree, but say that you can do it magically at an instant, then you transmit information, and that shouldn't be surprising. It's doing a non-local measurement. But I agree, yeah, for sure. To implement one of these, you need to do local measurements and then transmit information, yeah. Now, the other example is, consider a quantum field and some state for the quantum field, and then perform a local unitary, say, in this region of space-time, right? And then do an ideal measurement. Now, an ideal measurement is infinite dimensional. Is the one thing that the theorem that I showed you before implies is that something that is ideal, that gives you an outcome, cannot be localized. So that is applied in a whole horizontal slice of space-time. Now, of course, if in the same reason as before, there is a non-local projection, and this non-local projection makes it so that now B knows about what you did on A, even though it shouldn't know, because their space is separated. Okay, that's the issue he identifies. If I were able to do a measurement in which I measure the electric field 42 volts per meter, and then I do a projection over what would be the projector associated with the 42 in a spectral theory way of thinking, I'm doing a non-local operation, and I don't have salvation here, because this theory where you're doing it is relativistic, meaning you're not allowed to invoke something from outside. It needs to be internally consistent. It needs to be relativistic. So there's an inconsistency in the theory between being able to do ideal measurements and remaining relativistic by axiom. You know, part of your axioms is that you are imposing relativity. Make sense? Okay. Next. So one would say, well, maybe if I don't do ideal measurements, you see, in the lab, it's never a definite number. There's error bars, it's fuzzy. So the problem is that it's not really ideal. Well, let me tell you that, like, can we solve this by disallowing two non-local kinds of measurements? No, this is this paper, very nice paper. All of them are very nice, to be honest. Impossible Measurements Revisited, where they showed, no, it's, I mean, kind of common sense. Proving it is non-trivial, but it's kind of common sense. As long as you can, if you have projective measurements that are blurry, localized not at a point, if you want, then you can have a setup like this, where you can do exactly the same construction as Sorkin. And this thing is not delocalized in a whole slice of spacetime, but in localized regions of spacetime. Okay. All right, so the problem is there. So now, I was a PhD student when this, oh, please.
Could you argue that, I mean, whenever we talk about a measurement in the real world, it involves the interaction of some system with some probe. And I guess one of the, I don't know, maybe the fundamental assumption of QFT is that all interactions are local. So couldn't you get out of the problem that way by saying that
Partially,
whatever probe you use was always going to be locally probing some local property? And if we're claiming to be measuring something that is distributed and local, like an electric field of a box or something, if you want to measure it distributed over the whole box, you have to make sure the measurement lasts enough time that you're probing the field for the thing.
Yes, that's what that's part of my research lengths, trying to do that. there are issues that appear when you try to do that too. It's non-trivial too, if you really want to do the foundational microscopic structure of that. But yes, I agree with you. We can postpone this discussion a little bit later.
Okay,
Yeah,
I want to get the answer.
yeah. Well, I mean, maybe the answer is not, there's
Yeah,
no satisfactory
get
answer.
there.
yet.
There's another question.
Sorry, yeah.
So this argument, should they propose non-ideal measurements, so these are our measurements?
They're POVMs in general. And in fact, in this paper, they identify what POVMs would be okay with the coastal structure. And they not only show that naively done like this, they would violate causality. They actually identify the sets of POVMs that are okay with the coastal structure. It's not saying, this paper doesn't say there's no measurements that you can do to a quantum field. It's saying the set of measurements you can do in a quantum field is restricted. And it's restricted in a way that's non-trivial. If you just naively say, I measure this, and one of the things that I will say is that what you were saying about local measurements and detectors, right, a real interaction between systems, by doing those, you get one of those classes of POVMs that don't violate causality. But this is spoiler, so we'll get there. Anything else? Okay, this is a note that is scientifically less interesting, perhaps, but personally very interesting for me. So I always tell it to give credit where credit is due. I was a PhD student. At the time I was in Nottingham. And there was this paper that came out, and people working in RQI was very, I don't know what to call it, startled by it, which was this. It's kind of 2 pages, or it's very little. Faye Dowker, she's amazing, by the way. I don't know if you know her, but if you don't, totally recommend to read what she does. The paper was titled Useless Qubits in Relativistic Quantum Information. It's a very powerful title. And it says, I draw attention to previous work, that is Sorkin's paper, by the way, that shows that the observables corresponding to relativistic quantum field modes, commonly employed in papers on relativistic quantum information, by the way, but also in quantum optics, when you say a field mode, at least in a cavity, right, cannot be measured by ideal measurements. So basically it points to the Sorkin paper. That's basically what he did. At the time, in RQI, we were doing a lot of that because there was a big influence from how things were done in condensed matter and in quantum optics. So when I read this note, I said, well, I need to do something else. Some people, okay, there are many ways people have different reactions to it, but I abandoned doing the kind of stuff that was being done before. And I started to read about light matter interaction, meaning like, well, I mean, in the lab, I talked with whether John Maloko was in there, who is a guy who did particle detector models in the beginning to do in not the usual way that they're used with transition rates, but like, let's look at finite size, finite localization. And then papers on light matter interaction, John's papers as well. So that's where I started to look, okay, maybe there's other ways to approach this issue related to what you were saying, like, well, maybe we need to actually model the measurement differently, not just idealize and see what comes in. Okay, so there are not only 4, but these are the 4 that I know the best, and I think I would say those are the main 4 approaches to the measurement problem in QFT. I'm gonna only talk about the Fuster-Berg framework and the detector-based one, which is the one that I'm doing. But I'll mention that there are others. Robert Ockel, extremely promising, in my opinion, as well. There are some more recent papers that I should have put there. But it's related to what about having objects that are similar to projectors, like a little bit relaxed, and finding the POVMs and trying to connect maybe the opposite in philosophy to this, but similarly oriented. Here is, let's look at the light matter interaction properly described and see what sets of POVMs on the field they induce and how do you translate that to measuring the field and updating the field state, which is what I want in the end. This one is the opposite. It's more, what are the nice sets of POVMs, and among them, let's find the ones that make physical sense. In a way, I mean, summary, very, very fast summary. I really recommend. Robert Ockel is doing great things in this. And then there's the Fuster-Berg framework. Let me talk about Fuster-Berg, which is amazing, by the way. Yeah, I also have here Maria, is a former student of mine that brought with Doreen Fraser this. Things have been, this field is changing fast, but up to 2024, they did a great summary of the issues and the proposed solutions. And it's called Eliminating the Impossible. I love the philosopher's titles, to be honest. They're amazing. Recent progress on local measurement. Anyway, yeah. But anyway, let me talk. I'm going to talk about the Fürsterberg approach and the detector-based approach a little bit. Fürsterberg just a little bit, because Fürsterberg is elegant and solves the problem. But in my opinion, there's more to do. There's more work to do. What do I do? What do I want from a measurement theory in QFT, right? So I'm going to give you a set of desirable properties, and you tell me if you disagree with any, okay? So I wanted to be able to produce definite values, which makes sense. Sometimes experiments give you definite values, right? Like a Stenger-Lach experiment. I need an update rule. You see, that's the part that sometimes people don't care that much about, because then you do a measurement and then you reset the system, you destroy the system. But what if you don't? You want to do sequential measurements. There are a lot of foundational experiments that you need that, from the Zeno effect to Wigner's friend to the delayed quantum eraser. Measuring matters. The effect of measurements matters for fundamental physics. So I need a way to update the state of the field once it's measured. I need that update to be consistent with the theory. For example, respect covariance and respect causality if you're talking about a relativistic theory like QFT is. And you need to model experiments. You need to be able, your theory cannot be as abstract as, okay, I solved the problem on paper, but I don't know how to translate it to an experiment or a concrete implementation. It needs to be able to model experiments. And I think those are, I think they're reasonable, but I'm open to disagreeing. Okay, so let me talk about Fürsterberg. What is this formalism? So the formalism here is that, all right, let's try to do a full QFT description of the measurement problem. And what is that? I'm going to have a probe field and a target field. So my detector or my system measure is another quantum field. And the idea is, oh, I removed that slide, I think. Okay, but I'll tell you, the idea is that, maybe I can draw it. Space-time, I have two fields in this space-time. The two fields are not coupled, except for some region somewhere. And in that region, the two theories interact. I let them interact. And then in the causal future of that region, I assume that I can access the information in the probe field. So there's a target field that you're measuring, and you measure it through another field, through interaction. Now, it's all within QFT. Everything's relativistic. Everything's local and relativistic because it's all QFT. And they can describe how to measure asymptotically any observable, in the sense that they can compute. If I give a localized observable, I can tell you how to do the interaction and what to measure in the other field to have the induced observable to get information about the other observable asymptotically. It's kind of a S-matrix philosophy. So it's great. It does solve the problem like that. Of course, you can. If you use a field to measure another field, everything's relativistic. You don't have the issues that you have. Nobody projected anything here. What are the limitations that I see? Well, so what is a physically localizable probe? So the idea here is that you say, well, I have an interaction that is localized here, but how? How are you modeling that? Like, is that an atom, for example, described with QFT? But an atom cannot really be described by QFT with our current tools. We don't know how to do bound states in QFT. We can do effective theories, but those violate relativity at some scale, right? So how do you do it? How do you describe this physically localizable probe, right? And the other one is that there's no straightforward general way to relate it to experimental setups. Like if you're doing something in the lab and you have a photodetector, how do you relate that with this? What is the field that the photodetector emerges from, and how? There's also the issue that, this is just me being a bit pedantic, sorry about that. Who measures the measurer, right? The probe is still a quantum field. So if you want to extract information from the quantum field, you need to measure the probe. And we just discussed that there's a problem with measuring quantum fields, right? So yeah, those are the, let's say, limitations of the formalism. Don't get me wrong, the formalism is fantastic. And I totally recommend reading it. And it's extremely related to what I'm doing. In a way, being let's say, radically honest, and the things that we're doing are related. They're kind of particular cases of this, but we'll see. Yeah.
So I guess the picture that this paints is that the fields are fundamental. But what if we take the picture that matter is fundamental?
define matter, and then we talk.
Well, matter, this laptop is made of matter.
It's made of atoms, if I look, and
Exactly.
atoms are described by the quantum fields, no?
Exactly. So in quality, I guess. Okay, so again, I'm a lowly experimentalist. I can imagine that probing fields with other fields that are an electromagnetic field or something like that is more challenging than saying that my probe is an atom with atom field or
I
100 atoms.
I couldn't agree more with you.
So I guess, but I also know that obviously atoms are made of protons and electrons, and there's quantum fields that describe those. So I guess, how does this intuition manifest in this formalism, which kind of is agnostic to the field?
It is agnostic. This formalism does not tell you. It tells you that they assume. So there's a quote that I love by Fuster. He's great, that says, well, the assumption here is that somewhere someone knows how to measure something about the probe field. So that, and I don't mean in a bad way. It's like that the assumption is that there's, okay, he's proving that you can formally do it if you're able to access at least one probe field.
I think therefore I am kind of like that.
Yeah, kind of a little bit. I don't know. I mean, I want to make sure that I'm fair. Like the work is fantastic and sets up the basis to algebraically describe some structures like this, if you have it. Let me tell you this. If somebody tells you, here's a QFT description of an atom, this solves the problem.
Why is that?
Bound states. We don't know how to do bound states in QFT proper. They're so the problem is that QFT, interacting QFT is very tough. So you have a free QFT, things are okay normally.
Again, it's scattered.
That's right. So scattering theory is so bad from foundational speaking. The assumption is that you have, imagine, free electrons in the far past, that they don't interact at all, plane wave-like. Then they get to an interaction region, they interact a bit through the electromagnetic field, and they scatter away. But a free electron doesn't exist. An electron is always coupled to the electromagnetic field. If you were to describe an electron with a plane wave and a free field and doing that, you get problems that are called infrared divergences, because you have, in reality, you have rest states. I mean, you cannot describe particle physics. Particles don't exist. Let me put it like that. I don't believe in particles. If you really, really want to describe things with particles, you're gonna face problems. Yeah. So if you want to do a bound system, something localized that is bound, the only thing that we know how to do halfway is positronium, which is an atom where you have a positron and an electron that is unstable. An atom, no, it's very tough. It's just technically, it's not, the formalism allows for it. It's just technically we don't know how. Sorry, I don't have a better answer. That's what it is. Let's move to the particle detector approach. So how about using particle detectors? How do we measure quantum fields? Well, in the lab, as been mentioned here, people measure quantum fields with particle detectors, like a photodiode. That I have that. And what are particle detectors? Let me give you a definition and see if you agree with that. A particle detector is a non-relativistic quantum system that couples locally to the field. What do I mean by non-relativistic? Well, to a good extent, you can approximate the internal dynamics, not the motion or anything, the internal dynamics with non-relativistic quantum mechanics. Think of an hydrogen atom. There's no need to add relativistic corrections to a regular hydrogen atom in regular conditions. System is of course relativistic, but it admits a good non-relativistic approximation. Let me put it like that. And I have Andrew here, Bill Andrew, saying that particles are what particle detectors detect. Like particles just don't exist, I would say. I have this. I'm not gonna. Maybe I already showed you this when I came here. Maybe we can read it for fun. That's Willis Lamb wrote this paper in 1995, and you know Willis Lamb wrote you, right? The Nobel Prize, one of the founding fathers of quantum optics. And he wrote, "It should be apparent from the title of this article that the author does not like the use of the word photon, which dates from 1926. In his view, there is no such thing as a photon." Maybe we can leave it there even. But it says, only a comedy of errors and historical accidents led to its popularity among physicists and optical scientists. I admit the word is short and convenient, and its use is also habit-forming. He would use the word, even though he didn't like it. Similarly, one might find it convenient to speak of the ether or vacuum to stand for empty space, even if no such thing existed. There are very good substitutes for words for photon, like radiation or light, and for photonics, e.g. optics or quantum optics. Similar objections are possible to the use of the word phonon, which dates from 1932, and now the key point, right? Electrons, neutrinos of finite rest mass, or helium atoms can, under suitable conditions, be considered to be particles, since their theories then have viable non-relativistic and non-quantum limits. That's the key. If you cannot move to the comoving frame of your particle, then the description of particle is going to be bad. You cannot localize massless fields. Okay, we will have to discuss what you mean by a particle. If you mean a plane wave, then of course it's not real because it doesn't fit in your lab. If you mean a localized wave packet, then your particle, your single one Fock state, if you really say and you claim you generated a one excitation Fock state, let's not call it photon, just hide, so not to get Will Islam mad. We say a one Fock excitation wave packet that you have in your lab. That doesn't fit in your lab either. The tails of that cannot be very suppressed. So what you have in the lab is not quite that. It may look a lot like that, but it's not quite that. Anyway, this is just for fun. Let's get to the model, one simple model of light-matter interaction here that is called the Andrew DeWitt model. The Andrew, I wrote here a non-covariant. You can write this covariantly, there's no problem, but I wrote it in a given frame. The idea here is very simple. You have some internal degree of freedom of your matter, say it's an atom, hydrogen atom, that could be the dipole moment of the atom, because it's a scalar field that I have here with a monopole moment. And this thing is coupling to the quantum field linearly in a localized region. You see there's the support of this switching function and this mirroring function that identifies a region in spacetime. So the atom is seeing the field only in a localized region of spacetime. Okay. Now we can discuss about to what extent is a good approximation of the actual like matter interaction. Now there's non-trivialities, right? There's gauge issues. Of course, the scalar theory that simplifies a lot. There's the fact that it's a scalar field versus a vector field. But you can tell naively here, I mean, if you want a discussion, we did look into these things, and this last paper perhaps is one that we get more in depth about how these things emerge from not even that, like the actual minimal coupling plus gauge considerations of matter and light. But you can tell that if you consider dipole coupling, right, if you're into quantum optics, you would have seen the dipole coupling. This looks a lot like it, only it's a monopole coupling because it's a scalar field rather than a vector field. So if anything, take that. And then you see that the mirroring function is given by the wave functions of the excited and the ground state of your atom, right? That's where it's mirroring space. Right? Anyway, how am I doing time-wise? I'm almost done, no? Okay, I'll be fast. Maybe I'll summarize. So this is a bit more covariant. So you see this is the Hamiltonian density of this interaction. So you have a space-time mirroring. You have the monopole moment and the field. And the idea here is that, okay, this interaction can be made consistent with relativity. You say, well, the system is internally non-relativistic, but the difference is that we have scale control here. I can tell you how non-relativistic it is at what scales. So if you give me an energy scale, I can give you a description of the system that works without seeing any violations of covariance or relativity within those scales. Maybe I can accelerate this a bit and not go into the technical part by telling you the idea here is let's describe my measurements by non-relativistic particle detectors that couple to the field locally. And then I measure those detectors because internally they're non-relativistic. I can do projective measurements on them, ideal measurements on them, and that induces POVMs in the field. And those POVMs in the field that come from the light-matter interaction coupling, if you do it right, if you do it without the approximations that in quantum optics that break the relativistic nature of the theory, are within the POVMs identified in the impossible measurements revisited that are okay with the causal structure, with an asterisk. It's always with an asterisk. So I will, by the way, this also tells you that the update rule is contextual, kind of related to what was said before. The update rule is if you want an update rule over the correlation functions, although you can build a state as well. Server-dependent update rule. You can apply these things to relativistic versions of foundational experiments that are actually really cool in the results that we have when the regimes are within the relativistic regime, right? Anyway, I'm going a bit fast, but let me give you. So I could claim that the problem is solved, but it's not quite fully solved from the foundational perspective. Why not? This is Fuster speaking about our proposal. Yeah, it should be mentioned. So this is until very recently, previous work in RQI did not focus on induced system observables. Now, what the section was 32, subsequent to 2.4 has been increased interest in this direction. And a treatment of non-relativistic probes in a similar spirit to 2 can be found in 33, 34. This is us. So it's talking about our work. And it says, it should be mentioned. He's completely right, by the way. I don't disagree with anything Fuster says here. It should be mentioned that the coupling of non-relativistic structures to quantum fields typically requires either a singular or a non-local coupling, of which the latter is in conflict with causality. What is meant by this? What is meant by this is that you have two options. If you want to make it fully relativistic in the way that I'm telling you with particle detectors and light matter interaction, either you consider your matter point-like, then there's no problem whatsoever. You have 1 degree of freedom in a point of space-time or a point of space if you wanted to fix a foliation. And then there's no issue with causality. The problem that you have is that that's singular. You're going to have divergences if you do that. Inescapable. You can have perturbative series that don't converge, but leading orders are finite, but then you need to regularize at higher orders. Or another option is that your atom really doesn't live in a point. There's a wave function for it. It lives in some region of space. But if you do that, then it's saying, okay, you have 1 degree of freedom that is in many points of space at the same time. That violates causality and covariance. That is correct. So either you have to accept some degree of singularity of the model. I have it twice. I don't know why. Maybe it's because it's very important. It's not on purpose, but or accept some degree of control causality and covariance violations, meaning that, well, I have scales now and I can control my scales. And maybe we can, okay, because I want to tell you this message. The idea is that you can accept, if you discover matter, that you don't have infinite budget. So you would not be able to measure and resolve the UV, so very short distances. And at a given scale that you have, I can give you the model that would actually work with a violation of causality within those scales. I don't know how satisfactory it is, foundationally speaking, for if you're into the core of the foundations, but this is what we can do. And I will finish telling you about this one, which is an attempt to link the two. So we want particle detectors, the light matter interaction, emerging from localized QFT. I told you that bound systems are very difficult, and they are, but you know one thing that's not difficult? Modeling optical cavities. So I can have, here I have the Lagrangian of a scalar field that is confined by some potential that I assume goes to infinity. Think of a harmonic barrier, or think of whatever you want, infinite walls, I don't care. A confining potential. Now you have a confining potential. There's an example is the harmonic one. You have this equation of motion for the field. And of course, the solutions to that, we know them very well at the Hermite polynomials. Things are with exponential suppression. And we have a field theory that is fully localized in space. Well, fully localized, exponentially localized in space. You can fully localize if you do something wild, no, like infinite walls or something like that. And yeah, you have an infinite box, fully localized QFT. It's a QFT. It's fully relativistic. There's no approximation made here that violates causality or anything like that. There's a fully relativistic theory living in a region of space. So if it's a harmonic potential, tails that decay very fast. If it's an infinite box, well, you have it localized for sure. All right. So what can you do now? Well, if the potential is confining, right, goes to infinity at a finite, well, at a rate that is fast enough, then we have a discrete energy spectrum, right? And the idea, and I really want to finish, is that now I can treat the confined field as my detector field. So the Fuster-Berg kind of philosophy, let's take the field as a detector, and the field is now confined. Now, I cannot say I'm going to use a model of the field as my detector without reason, because that is at risk of running into the problems that were identified before. But what we can do now, we have a target field, phi, that we want to measure with a detector field, phi d. And they're interacting. And now they interact at some region of spacetime, same as the Fuster-Berg part, little thing. And the linear interaction with a finite spatial support, picking a foliation, you can write an interaction Hamiltonian density like this. Foliation is I don't know how familiar you are with GR, but the affiliation is pick a direction of time and pick the hypersurfaces orthogonal to that. So planes of simultaneity for some direction of time. This interaction is non-singular and local. 100% is a QFT, is two QFTs interacting with each other. And we can do calculations with it as opposed to a bound system. Sure, you can wonder, who is setting the potential? Well, I don't care. Someone somewhere knows how to set up a potential. Build a cavity. And you go ahead with that. Let me just go to the end. And you can do things like entanglement harvesting that I haven't talked about, but it's okay. So, okay, now what happens? Now I have my theory. Now this works on its own, it works. Now let me say the following. What if I have a finite budget to do this? So it might not have my cavity or my confining potential, but now as an experimenter, I'm not allowed to measure arbitrarily high energy modes for several reasons. What do you get then? And then let me just summarize a lot. You end up with, if you have only access to a finite number of energy modes, if you want, if you have a budget for energy, you end up with an interaction that has a spatial smearing in the same way the non-locality that Fuster identified. A non-local system emerges. Obviously, to have a fully causal system, you need to resolve the high energy physics, the UV. But if you don't resolve the UV and only have access to a finite budget of energy, you get something that is smeared. And the idea is that the detector, okay, actually, the effective interaction when you have only access to a small budget of energy reduces to a unrelated particle detector, reduces to the model of like matter interaction that I mentioned before. So the underweight detector, the matter models that we have can be thought of as emerging from the inability to fully resolve the UV in any given experimental setup. So this kind of connection allows you to rigorously talk about what regimes you can use simplified models to the same extent as fully relativistic QFT detectors a la Fusterberg and still connect with light matter interaction as is done in the lab. And I could talk about crazy things. I don't have the time, but maybe a different time I will tell you about more foundationally related stuff, because maybe when you have a relativistic theory of detectors, maybe you can think, can you rewrite the dynamics of space-time as a function of what experimenters would see in detectors? And maybe you can, maybe not, but I think I'll leave it there and we can have a discussion. Thank you.